relativistic heavy-ion collision experiments. So the two figures of merit in relativistic heavy-ion collision experiment are the two control parameters which we can control as a user, as an experimenter, is the parameters which we can control. One is the center of mass energy of the colliding nucleon pair and the atomic number of the colliding nucleon. These are the two control parameters which we can control. And the physics of relativistic heavy-ion collision is actually driven by the continuous improvements both in the accelerator as well as in the detector technology. So the game was started in the middle of 80s in 1984 when the beams of energy 1 to 2 GeV by C, beams of momentum 1 to 2 GeV by C per nucleon were available in Super HILAC into Brookhaven at Barclay. Then in 1986, there was a facility called alternating gradient synchrotron at Brookhaven, which basically accelerated silicon beams having a center of mass energy of 5 GeV per nucleon pair. Almost at the same time, at CERN, super proton synchrotron SPS facility, accelerated beams of oxygen and sulfur were available up to a energy of 20 GeV in the center of mass per nucleon pair. In the beginning of 90s, the gold nuclei were first accelerated at Brookhaven in the alternating gradient synchrotron. Again, the center of mass energy was around 5 GeV per nucleon pair, whereas the beams of lead were accelerated at CERN super proton synchrotron, where the energy was 70 GeV per nucleon pair. So we know that the fixed target has a limitation; it cannot go beyond to a maximum. That is the maximum. The fixed target machines, they have a limitation that you cannot go to a very high center of mass energy. So in order to go to a very high center of mass energy, a different design of accelerators are found that we all know. They are called colliders, where there is no target is not fixed to the left. There are both beam experiments. So the first collider, heavy-ion collider, was the relativistic heavy-ion collider RHIC at Brookhaven National Laboratory, which had its first gold collisions with 200 GeV per nucleon pair beam energy in the year 2000. And after 10 years, we had this lead collisions at LHC, which had a quantum jump in the terms of center of mass energy, which is almost 10 times, more than 10 times, in this which is 2.76 GeV or 2760 GeV. And in 2015, there are lead collisions at the LHC with even higher beam energy of 5020 GeV. Or 5, I think it is 500. There might be a mistake. It is 5.5 TeV actually. So just to tell a difference between the fixed target and the colliding beams. In the fixed target, the problem is that the center of mass energy is limited by if the E beam is the beam energy, which is the actual energy accelerated in the machine, but the reaction or the interactions occur in the center of mass square. And the center of mass energy is limited by E center of mass is square root of twice of 2 into Mn into E beam, where Mn is the mass of the nucleon and E beam is the beam energy. And this is there is one task for the student just to prove this relation. This can be very easily proven using the notation of 4 momentum. And I think you will also work it out in your relativistic analysis. So the highest ever achieved energy in a fixed target machine is at CERN SPS with a beam of 160 GeV per nucleon. This corresponds to a center of mass energy or of the order of 20 GeV per nucleon pair. Actually, if you work it out, it will come around 17 point something. So roughly we will say this is around 20 GeV per nucleon pair. However, one advantage of fixed target experiment is that you can have a very high beam intensity or high luminosity, which leads to high interaction rate. Again, you can think it of why you can go to a very high interaction rate or high luminosity in fixed target experiment, and of course this is not possible in the colliders. So the colliders advantage is that you can go to a much higher center of mass energy, which for a head-on collision the center of mass energy is just the energy of E1 plus E2. So if two beams are identical and moving with the same energy, then the total energy, center of mass energy, is just twice the energy of the beam. Okay. So the highest achieved is up till now is the for heavy-ion collisions. Of course, for lead beams, it's 5.5 TeV per nucleon pair at the LHC. However, the challenge in collider experiments, the disadvantage of the collider experiments is the lower luminosity, which leads to low interaction. So the two heavy ion colliders which are at operation, which are colliding heavy ions, is RHIC and LHC since 2000. And you all know, Viranga has already discussed that presently present program of RHIC is not only initially, though RHIC was not designed for lower energy, it was designed for 200 GeV good collision, but now with the aim to map the QCD phase diagram, it has taken up a program called beam energy scan, which has also in different phases, and it will come down up to I think 7 GeV in collider mode, and then up to 3 GeV in center of mass with a fixed target. Also, there is an LHC which is being operational at SAM since 2010. Already you have collected data in run 1 and run 2, and we all have got mail that the run 3 has the program for run 3 has started very recently. Data collection for run 3 has started recently. Now, in a particle accelerator, for any particle accelerator, the maximum energy of a proton beam is always EP. And if suppose the maximum energy for a proton beam is EP, that is the maximum energy up to which a proton beam can be accelerated. In the same machine, you cannot accelerate a heavy ion up to that energy, up to the value of EP. The maximum value up to which you can accelerate a heavy ion depends on the charge by mass ratio. The mass, atomic number and mass number of the nucleus. And it will be just Z by A times EP. So can anybody tell why this is so? Can anybody tell why this is so? Why can't from in the same machine from the heavy ions I cannot go up to EP, but it is Z by A times EP? Any student? Dukishan?
Sir, I know this conversation, but why maybe this Z by A, I don't know. Because it in the case of nucleus is not, if it is not linearly superimpose of proton, that way maybe we think.
Basically, what you are telling, you are going in the right direction. Anybody else wants to try? I have some names sitting in yesterday's discussion. Hamgorat? Priyanshi? Okay, so what Dukisham was telling, maybe you can also think it out, but let me just tell you the answer. Because when you want to accelerate a nucleus, so you have to basically accelerate both the neutrons, and basically you have to energize the entire nucleus. However, how to do this acceleration? Ultimately, you do the acceleration by putting the charge particle by applying an electric field. Now, applying an electric field, you can accelerate the protons, but not the neutrons, because neutrons are charged neutrons. Okay. So if EP is the maximum energy, you can accelerate the proton, which is a charged particle. So for a nucleus which has Z number of protons in it, so the maximum energy you can impart to it is Z into EP. Because for a single proton, you can do up the maximum energy up to which you can accelerate is EP. So for a system which has Z protons, the maximum acceleration you can impart applying the same electric field, it's Z into EP, because it is only the protons which will feel the electric field and will get accelerated. However, when it comes to when we talk about the energy per nucleon, because then you have to consider both neutrons and protons accelerated, because the total mass will come, because ultimately you are accelerating the entire nucleus, right? So when it comes to the energy per nucleon, so then it will be Z into EP by A. In the denominator, that is why there is A. That's why there is A. Okay, the entire mass of the nucleus. When you want to talk, because Z into EP is the total energy of the total energy, total acceleration of the nucleus. But what we always talk about energy per nucleon or per nucleon pair. So that means you have to divide the total energy acquired by the nucleus by the total number of nucleons present in the system, because they are all there in the nucleus. No? So that is why you are dividing it by A. So that is the reason why it is Z by A times EP. You will immediately understand it. For example, if you take, for example, SPS. In SPS, the maximum energy to which a proton beam can be accelerated is around 400 or 450 GeV. That is why if you look at some PA programs of PA programs in SPS, there are experiments called NA50, NA60. So the maximum energy, the energy at the PA program, they are basically proton nucleus collisions. Where there is a proton beam incident on a nuclear target. So the energy of this proton beams are 400 GeV or 450 GeV. But when it comes to the lead-lead collision, heavy ion collision, lead-lead collision, the maximum energy of the for this lead beam was not 450 or 400 GeV, it was 158 GeV. If you just put instead of if you put 450 and instead of Z and A, if you put 82 by 208, you will see you get similar values. You will get similar values. Okay, that is why you can have the maximum energy for a heavy ion collision at SPS is around 150 GeV beam energy, whereas for lead-lead collision, similar will be the case for indium-indium collision, whereas for a proton the maximum energy was 400 or 450 GeV for PA collisions. Similar thing you can calculate. For example, what is the center of mass energy? For P-lead collision, right? So you know energy of one proton beam, you can calculate the energy of another lead beam, which will be, so it will be EP plus Z by A into EP. And you will see, you will get the value, whatever is the value. I forgot. I think it is 5.02 TeV or something. So I don't remember it by heart. You can just calculate. Okay. Clear the picture?
Yes, yes, yes.
Okay, I hope this is clear to others also. Otherwise, if you have still your doubt, you start thinking, and you still have doubt, we can discuss it again tomorrow. So I will just briefly discuss about the highlights from the RHIC heavy ion program and the LHC heavy ion program, because RHIC is the first collider, and we are having the STAR Alice India School. So that STAR is one of the major experimental programs actually. So the major findings of RHIC is that what were found is the azimuthal anisotropy of the particle production at low PT. By low, it means PT value less than 2 GeV by C. And the results are interpreted as a collective expansion of the partonic medium of the QGP medium. And it has been shown that the ideal hydrodynamics, non-viscous ideal hydrodynamics, is very close to the data. And application of viscous hydrodynamics basically have indicated there is a very small viscosity over entropy density, which basically means that the produced medium doesn't behave like a gas, rather it behaves like a liquid. So this is called a strongly coupled Quark-Gluon Plasma, or we talk about SQGP, or perfect fluid. And there is the evidence of early thermalization. The thermalization or the QGP thermalization or the QGP formation type is of the order of 1 to 2 February by C. Also, this basically all these findings basically tells you the produced medium show collectivity. The produced medium show collectivity. Okay, and then at high PD there is something called hadron suppression or jet quenching. So which basically tells that the medium is to large extent opaque for jets, which basically tells you that its high PD jets are suppressed, which can only be possible if you have a very dense medium. If you make some back calculations that to explain the data of the observed suppression of these jets, the densities you require is very high compared to the limiting density of hadrons. The densities are so large, densities of the medium are so large that the constituents cannot be hadrons, because hadrons cannot survive at that very high density. So ultimately, what comes out that it is a very highly dense colored or gluonic medium that could lead to the suppression of the high PD hadrons. So together they tell, and then the yield of the hadron species in chemical equilibrium with freeze out temperature TCH is close to TC. TC is the critical temperature or pseudo-critical temperature or the crossover temperature working finds for the lattice QCP. And the analysis of the yields within a statistical hadronization model built within this grand canonical ensemble framework tells you that TCH is roughly of the order of 160 MeV. So all this together tells you that at RHIC you produce a partonic medium which shows collective properties. Now, if we remember the definition of Quark-Gluon Plasma, that it is a collective properties can only be shown. Partonic medium shows the collective properties. And if you remember the definition of Quark-Gluon Plasma, it basically tells you that it is a medium made up of quarks and gluon, that partons, and it shows some plasma properties like collectivity. So ultimately, the outcome is that at RHIC we have produced QGP or Quark-Gluon Plasma. So what are the outcomes for the heavier results from the heavy ions at LHC? So the results are mostly qualitatively similar to similar results in heavy ion lead-lead collisions compared to what we have observed in gold-gold collisions at RHIC. So we do see the jet quenching, we do see the elliptic flow, and the analysis of this particle yields, it has been shown that particles are in thermal equilibrium, or they are very close to the chemical equilibrium, or very either they are in chemical equilibrium or very high heavy particles. They are close to equilibrium values, and there are hints of Jebshire regeneration, but with Ceylon suppression, so which are basically related to a phenomenon called device screening. So we will discuss that maybe in the next class. However, the main surprises from LHC have not come from the heavy ion collision or from the heavy ion. Rather, they come from something which was never that important, which is the proton in the context of heavy ion physics, that is the proton-proton and proton-lead collisions. Traditionally, as you know, these proton-proton collisions are generally used as a baseline or a reference to your heavy ion collision, with respect to which you try to look the medium effects in heavy ion collision. Similarly, the proton-nucleus collision, like proton-lead collisions, they are basically used to understand the effect of a cold nuclear medium. So once you measure some observable in PP and P-lead collisions, then they basically tells you how the PP collisions are basically considered equivalent to vacuum, and P-lead collisions are considered equivalent to the presence of a cold nuclear medium. So you basically know how the observable behaves in vacuum and how it behaves in a cold nuclear method, in a cold nuclear medium. Then what will happen? They helps you to isolate the genuine hot medium effects, the produced medium effects, which can be seen in a nucleus-nucleus collision. In the nucleus-nucleus collision, what you have, because you have a convolution of all possible effects. There can be effects in vacuum, or there can be effects of cold nuclear matter, and on top of that, there is a effects from the hot medium. So all are convoluted in the data. So to subtract the cold medium effects, these PP and PA collisions are used. And if you just subtract the effect of PP and PA from the AA data, if there is something is remaining, that can be genuinely attributed to the produced hot medium. And looking at the characteristics of the medium, you basically decide that this medium is basically a partonic medium or a hadronic medium. Okay, so that is why the PP and P-lead collisions are traditionally used as for your baseline reference measurements for your AA collision or a heavy ion collision. However, in the LHC, particularly the high multiplicity PP collisions and P-lead collisions they have come with a surprise which was never seen before. So there was an observation of elliptic flow, and there are other effects like formation of ridge, some structures in two-particle correlation, which were very specific before the LHC era, which were very specific to your heavy ion collisions. They were seen in PP and P-lead collisions. But does that mean QGP is produced even in small systems? However, one of the observables, very prominent observable of QGP production is jet quenching. Okay, but up till now, jet quenching have not seen in small systems. So this is still a question of ongoing discussion or debate whether we see the small droplets of QGP in PP collisions or not. If we have time tomorrow, so we will have a discussion on this. So now, before we go to a detailed discussion, we will have just quickly, we will just brush up our basics, because that I believe will help us to understand the behavior of the observables, or that will be helpful to the new students who may be taking the school course for the first time. So mostly we use natural units in high energy physics. We generally use natural units. In natural unit system, basically you set H equal to C equal to kV. Kv is the Boltzmann constant equal to 1. Okay. to set their values to 1 in this unit system. So as a result, all speeds are just measured as a fraction of the speed of light, and they have no units. The speeds are dimensional, are unitless, because speed you express always in terms of v by c. Okay, so our beta since c equal to 1, your beta becomes equal to v. So your speeds become dimensional, have no units. Also, the Einstein's equation simplified E equal to gamma n, because and E square is P square plus N square. So you don't have to carry all the powers of C. E square is P square C square plus N square C to the power 4. You don't have to carry all these things. You just have E square equal to P square plus N square. Similarly, de Broglie's wavelength, instead of P equal to h over lambda, you just write it P equal to 1 by lambda. Or kinetic energy of a particle becomes equal to the temperature, because if the kinetic energy of a particle becomes equal to the thermal energy, you write E of the order of kBT. Okay, but since you set kB equal to 1, your energy and temperatures have the same dimension. So E and T are same. Okay. So in other words, energy has the units of GeV. Mass has units of GeV by c square, but you put c equal to 1, so mass also has a unit of GeV. Momentum you can use either in GeV or if you put c equal to 1, so momentum has units GeV. But many a times you will see in the papers that people would like to carry this c, so they write the momentum in terms of GeV by c. So distance has the unit of GeV inverse. Okay. Distance as a unit of GeV inverse, this directly comes from the uncertainty relation, or even from de Broglie's wavelength, that if P is 1 by lambda, that means lambda is measured in terms of length scale, where P is now have the same dimension as of energy, so that will be measured in terms of energy scale. So P will be in GeV and lambda will be GeV inverse. Okay, time also has a unit of GeV inverse, because you know distance is speed into time, but then speed is unitless. So distance and time have the same unit. Okay. So now a little bit of kinematics. So the variable we just discussed the variables which we often use in our next set of slides in our next part of lecture. But you will have a detailed course on kinematics. I think Gamuda will teach you in your subsequent days. So the transverse momentum Pt is nothing but P sine theta. So you generally assume the beam along the z-axis. The axis of the direction in which beam is moving, you take that direction as the z direction of the z-axis. So if a particle is coming out, or a particle is produced with a momentum p with respect to the z-axis, so then your pt is p sine theta, and of course pl is p cos theta. Then you define transverse mass mt, because you know is mt equal to square root of pt square plus m square. Okay. So the rapidity y, rapidity is additive under the Lorentz transformation. The rapidity you define as tan hyperbolic inverse beta L, or equal to 1 plus beta L by 1 minus beta L, where beta L is the longitudinal velocity of the particle. And you can show that beta L is basically PL by T. So if you put instead of beta L, the longitudinal velocity beta L is equal to PL by E, then if you put that, so you can come from here to you can come to a relation half of ln E plus PL by E minus PL. Also, you can express E as mt cos the hyperbolic y, and Pz E is the energy of a particle, mt is the transverse mass, y is the rapidity, and Pz as mt sine hyperbolic y. Okay. Similarly, as I said, since the rapidity is additive under Lorentz transformation, you see generally we use two reference frames of reference in relativistic heavy and collision experiments. One is called center of mass frame, one is called laboratory frame. So for a particle, you can show that for the particle, the rapidity of a particle in the left frame, if I call it YL, and if the same rapidity of the same particle in the center of mass frame, if I call it YCL, you can show that one can write YL equal to YCL plus Y frame. So rapidity of a particle in the laboratory frame is equal to laboratory of the same particle in the center of mass frame plus the rapidity of the frame itself. Now all these frames are inertial frames, right? That means this frame, what are the inertial frames? That means the frames which are moving at constant velocity with respect to each other. That is why this frame rapidity is a constant. So if you make dy lab, so then dy lab should be equal to dy center of mass, dy CMS plus dy frame. But since y frame is a constant, why y frame is a constant? Because beta frame is constant. The velocity of the frame velocity is constant. Hence, the frame rapidity will be constant, which means dy frame will be 0. Which basically tells you dy lab equal to dy center of mass. So, a number of particles number should be a Lorentz-invariant quantity. It should not change from frame to frame, right? So, ultimately one can show that d and dy is frame invariant. Okay. However, there in many cases it is not very difficult to measure rapidity, because to know the rapidity, you need to know the longitudinal momentum of the particle as well as the energy of the particle, right? You have E plus PL and E minus PL. And what to know the energy of the particle, you need to know the momentum of the particle as well as the mass of the particle. That means you need to identify the particle. So very often, instead of rapidity, we use another variable which is called pseudo rapidity. Pseudo rapidity is defined as eta. We define it by eta, and you write it as 1 plus 1/2 ln p plus pl by p minus pl. You replace E by P. Okay. So you replace E by P. So which you can write as half ln 1 plus PL by P divided by 1 minus PL by P. But what is PL by P? PL by P is nothing but cos theta. So you can come up with half ln 1 plus cos theta by 1 minus cos theta. And if a particle is ultra-relativistic, by meaning ultra-relativistic means its kinetic energy or its momentum is much greater than its rest constant. So in that case, your energy and momentum will be equivalent. So you can write your rapidity also as half ln. Instead of E will be nearly equal to P. So if you write Y nearly equal to half ln P plus PL by P minus PL. And then you can write it as half ln 1 plus cos theta by 1 minus cos theta. And if you apply some trigonometric relations, you will see this is nothing but minus ln tan theta by 2, which is a pseudo rapidity. So here, sorry, there is a typo. So this P can be written as Pt cos hyperbolic theta, and Pz can be written as Pt sin hyperbolic. Remember, unlike d and dy is frame dependent. D and dy was frame independent, but the shape of the rapidity distribution is same in the center of mass frame and the lab frame. Only it will be shifted because the rapidity distribution, rapidity is additive under Lorentz transformation. So the shape remains the same, only its peak position generally shifted, or its center generally shifted. So when you go from laboratory lab frame to the center of mass frame. But this is not true for pseudo rapidity distribution, D and D. This is a frame dependent. And then there is a question you can consider how dn and dy and dy are connected. So one can show that they are connected because there is a coordinate transformation from y to eta, and these two distributions d and dy and d and theta are related to some Jacobian. Okay. So that also you can try to see what is that Jacobian, how d and dy and d and theta are connected. So one question here I have asked that what is the advantage of eta over y? So you can think of, maybe most of you already know this. And then another question is that you can also show that E d3n by d3p, this sometimes we call it triple difference, is a Lorentz-invariant quantity. This is the quantity what we measure in the experiment. This is known as triple differential invariant cross section. So why this is called triple differential invariant cross section? Because we have a triple differential, and invariant means because it is invariant under Lorentz transformation. So if you measure it, it remains the same in the center of mass frame as well as in the lab frame. So how will you show this? Okay, so this remains as an your exercise problem to do the assignment problem to prove this. This is, and also I think you will discuss it in more detail in your kinematic course. So this is the relation between eta. So eta equal to 0, that is the mid rapidity or mid pseudo rapidity, is a perpendicular, is a 90-degree relation. And as you increase eta more and more eta, you go closer and closer to the deep pipe. So this is a small bit about the kinematics. There is another thing which we need to know before we go make progress is about the centrality of a collision. So how do we decide the centrality of a collision or centrality of an event? So as you know, when you collide two nuclei, the nuclei are accelerated to the relativistic speed along the z direction. As a result, they undergo Lorentz contraction because there is a Lorentz contraction of length along the z direction. As a result, you can assume the nucleus to start with a spherical, but now its length along the z direction will be contracted. So in the x and y, it has its extension will be, its radius will be RA in the x, RA in the y, because it is a sphere. But in the z direction, this will be highly contracted. So what will be the amount of contraction? It will be RA by gamma, right? Gamma is the Lorentz contraction factor. We know that L goes to L by gamma, the results of Lorentz contraction. So along the direction of the beam, it will be RA by gamma, which is the z direction, but there is no contraction in the xy direction because there is a perpendicular to the motion. And we know from the Lorentz transformation equation, quantities remain same in the direction perpendicular to the velocity of the frame velocity, right? So basically, they will look like more like a thin disc or thin cylinder. So that means you have a circular profile, and then it gets contracted along the longitudinal direction. So when two nuclei collide, this is basically, you can consider the collision between two circular discs. Now, impact parameter is something which is basically defined as the perpendicular distance between the center of the two nuclei. So if the two nuclei collide head-on, one just on the other, this B will be 0. Their centers will be on the same line. And if they collide, so this is called the central collision. On the other hand, the B could be such that J will just grazing at each other. They can collide at grazing angle. One is here and one will come here. In that case, B will be just equal to 2RA. Radius RA plus RB, RA is the radius of the nucleus. So in case of this is known as peripheral collision. In case of ultra-peripheral collision, B will be of the order of 2RA, right? So because if we consider the collision of identical nuclei, and if they are not identical, then it will be RA plus RB, the sum of the radii of the two nuclei. This will be clear if you look at this picture. So B is called the impact parameter of the collision. So those of the nucleons from these two colliding nuclei which take part in the collision, that means the nucleons which are residing here or the nucleons which are residing here in this overlap zone. These are the nucleons which will take part in the collision. They are called participants, or sometimes they are also called wounded nucleons. What is meant by participant? Because they participate in the reaction, in the collision. Okay, and the nucleons which are residing here, or for example here, they just look at the collision. They don't take part in the collision. They remain unaffected by the collision. Okay, they are called spectators because they are just mere spectators. They watch what is being happening, but they themselves do not take part in the collision. Okay. So the number of inelastic nuclear collision. So in the collision zone, the nucleons from the two colliding nuclei will collide with each other. So the end call or the number of inelastic nuclear collision is what is known as number of binary collision. So why is the number of inelastic nuclear collisions we are interested in? Because ultimately what we are interested in are the particle production in heavier collision, the produced particles. And we know from our definition, elastic collision of the collision in which new particles are produced. Elastic collisions are in which the new particles are not produced. That is why when we talk about number of binary collisions, what we basically mean is the number of new inelastic nuclear collisions which are taking place in the collision zone. And n part is number of nucleons which underwent at least one inelastic nuclear collision. So the inelastic, again, as we know that since we are talking about we are interested in particle production, what is important to us is that in inelastic collision, the participants are the number of nucleons from the two colliding nuclei which underwent at least one inelastic nuclear collision. So, if I now say, as I said, that there is a Lorentz, there is again a question. So that we have in a relativistic invariant collision, we have collision between two Lorentz contracted nuclei. So what is the value of this Lorentz contraction at top RHIC energy? What will be the value of this gamma at the top RHIC energy? Can anybody tell? Hero?
Yes, sir. Is it 200? Yes, sir. Can you tell me the question again?
So I asked what is the amount of Lorentz contraction at top peak energy? That is 200 GeV energy per nucleon pair. Root S Nn is 200 GeV at RHIC. So that is the top peak energy, right? So what is the value of gamma? The amount of contraction by which a particular nucleus is being, one gold nucleus is being contracted. Did you get the question?
Yes, sir, but I forgot the formula now.
Okay. Okay, so anybody else wants to try? Anybody else wants to try? Since not the case, okay, so then you can keep on thinking. If you don't want to try it now, so let's move onwards. So question is, how can we decide or how can we calculate the number, these quantities in the global model? For example, the number for a given impact parameter, how can we calculate the number of binary collisions in call a number of participants? So basically, the model which we take help to which we employ to calculate these quantities is known as the global model. The global model is being heavily used in the field of relativistic heavy physics. This is a purely geometrical effects and have no quantum effects or no dynamic effects. So what is the procedure? The procedure is that you randomly select, and what we use most often is the Monte Carlo global model. There are two kinds of global model. One is called optical global model, which was used earlier, and another global model called Monte Carlo global model, which is more recently used and which is the state of the art. So in Monte Carlo global model, what we do, we randomly select select some impact parameter B between 0 to 2 RA. So we randomly select some impact parameter and distribute the nucleons of the two nuclei according to the nuclear density distribution, like that is Wood section density distribution. Then you consider all pairs with one nucleon from nucleus A and other from nucleus B. You calculate how many pairs you can calculate, how many pairs you can have by combining one nucleon from nucleus A and another one from nucleus B. And then finally, you count only those pairs as inelastic nucleon together, and then finally to find the number of binary collisions, you have to find those pairs which have undergone inelastic nucleon collision. How do you know that a given pair of nucleons, taking one nucleon from nucleus A and another nucleon from nucleus B, have undergone inelastic nucleus collision? So what basically you calculate the distance between them. Okay. In the transverse plane, in the XY plane, you calculate the distance between the two nucleons. Let's call it D. And if D is less than square root of sigma nn by pi, okay, if that is this is, then you are consider that this is where sigma nn is the inelastic nucleon cross section. And you know the classical or the geometrical picture of the cross section. The geometrical picture of the cross section is sigma goes as pi r square. So that means if the distance between two nucleons is less than square root of sigma nn by pi, this basically implies that these two nucleons are within the sphere of influence of each other. So one nucleus is within the sphere of influence of the other to make inelastic collision. So those pairs for which you want to randomly distribute the pairs and you count all the number of pairs, and for those pairs for which the separation between them, the separation between the two nucleons XY plane is less than square root of sigma nn by pi. So those are the nucleons which have undergone at least one inelastic nucleon collision. Okay. You count those are by you repeat it many times, and then you can get an average number of participants. Also, you repeat it many times, and you can count how many number of such inelastic collisions happens for a given impact parameter B. So that will give you an average value of n. In general, this is a purely geometric model. Only dynamics comes in through the sigma n. Sigma n is a dynamical quantity, elastic nucleon cross section, which is not the same For example, at SPS energy and RHIC energy and LHC energy. So the dependence of dynamics, which you will see that this is rather a weak dependence, and dependence comes only through sigma error. Rest all are geometrical in your calculation of global model. So ultimately, we have to connect it to the experimental centrality classes. Experimentally, we measure centrality with 0 to 5% centrality, 20 to 30% centrality, 10 to 80% centrality. So ultimately, we have to basically calculate our theoretical estimations of global models to the experimental centrality classes. So experimentally, what we do, we measure the charge particle multiplicity, for example, using the V0 detectors analysis. And then we assume this N charge V increases monotonically. This N charge V, the charge particle multiplicity monotonically increases with decreasing V. And you define a centrality class by selecting a particular percentile of the measured multiplicity distribution. So this measured multiplicity distribution will be a negative binomial distribution convoluted with number of participants, and this is called two-component model with Fn part plus 1 minus F into N count. But F is known as the fraction of, it is called fraction of Hart functions. So you get a distribution like this. This is basically a sum of many entities. You get a distribution like this, and then you choose a particular centrality profile. Okay, and look what are the multiplicities for or multiplicity ranges for this particular centrality class. And then you basically use the global Monte Carlo method or model to find the impact parameter range corresponding to the same percentile. So depending on a particular multiplicity class, you assign a particular percentile or percentile B, a range of percentile B, and then you use the Monte Carlo global model to find what is the interval in the impact parameter space in terms of B min and B max, which corresponds to the same percentage. And then in that B min and B max, you calculate average N part and N part in the interval. So this is one example from the what has been used by the Alice experiment, the Alice data papers in 2.76 TeV lead collisions. And there the use this value of sigma n 64 MV and this plus minus 5 MV. And so here are the values of B min and B max, and you can see this average N part, and these are the RMS and the systematic errors in these calculations. So we will just see that, for example, how the charge, this is the charge particle multiplicity distribution. So this is charge particle multiplicity distribution. We will now talk about some global observables. So the very first thing what one measures is the multiplicity distribution. And this is a differential multiplicity distribution, that is Dn charge eta with a function of eta. And this has been measured at RHIC by the Phobos experiment at RHIC Accelerator at different center of mass energies at 19.6 GeV, at the 130 GeV and 200 GeV. And these lines are different centrality classes. Okay. So this is the maximum centrality, the top centrality, which is 0 to 6%. That is, this is the most central collision. And these are the least central collision or the more peripheral collisions of the measured centrality classes. So what we see, the charge particle multiplicity, we have plotted as a function of zero rapidity. So with increasing collision energy, we see multiplicity, the peak of the multiplicity distribution increases with increasing collision energy, which is expected that more particles are produced, and multiplicity increases with increment in the increasing collision energy. And of course, we have plotted different centrality, and this multiplicity also increases as we go from peripheral to more central. So these are the very clear indications of the increase in multiplicity with energy as well as collision centrality. So also what is important is the charge particle multiplicity eta equal to 0. Eta equal to 0 is where it is basically flat, or the peak of the distribution, where is the maximum of this charge particle distribution occurs. So how does the maximum this d enters d eta at eta equal to 0? The maximum varies with root s, with the beam energy. So this is basically the case. So the dotted line show this for PP collisions, and this is for central gold collision. As we see that d enters d eta show a power loss getting. This is one of the early important results from the LHC, or from the Alice experiment. But before that, it is generally assumed that the dHs deta scales logarithmically with beam energy. The multiplicity increases logarithmically with beam energy. Whereas it is first after the LHC beam band, after the results of LHC PP collisions are available, it has been seen that the multiplicity within elementary collisions scales as a power law. So it is a much faster increase than the logarithmic increase. Okay. So this dHs data show the power law scaling both for PP and for AA system. However, the increase in central gold collision is stronger than in PP. What does that mean? That possibly implies there is some special mechanism happening or some happening in case of AA collisions which are not present in PP collisions. So you can see likely as we have calculated the centrality, we have a beam energy dependence of charged particle multiplicity. Similarly, we can calculate the dHs deta, the centrality dependence of dHs deta, how the this depends on the centrality of the collision. And there are the numbers for both the 2.76 TeV lead collisions, which are from Alice experiment, and 200 GeV gold collision, which is from RHIC. And what we have seen, there is a relative increase per participant is similar at RHIC and LHC. Which basically, so once you dHs deta, the function of expert might be different, but when you calculate scale this dHs deta with the number of participants, what you see that the relative increase are same. They more or less fall on the same band, on the same line. Which basically tells you that this is a mere this increase. This is a geometrical effect. So the gold collision and lead collision, the geometry remains more or less same. Only the beam energy increases, your sigma energy increases. So the number of participants might be different. But once you normalize the scale with the number of participants, the centrality dependence looks more or less same for 2.76 TeV lead collisions and 200 TeV gold collision, which basically tells you that the effect you have seen is basically a geometry. So we can also calculate why this estimation of dHs deta is important, or dHs. You can similarly, once you identify the particles, you can also calculate the dEt dy or dHs dy. Not dHs dy. You can calculate the rapidity distribution for different particles. You cannot do dHs dy, of course, for obvious reasons. So once you identify the hadrons, you can have the d and dy for different hadrons. And there is a formula, which celebrated formula, which is called Bjorken's formula, from where you can calculate the energy density, initial energy density of the condition. Okay. And this, we have just put it the formula, we will not derive it in the class, and one can show that, and it has been shown by Bjorken that to evaluate this initial energy density of the collision, what you need as the input is the final state multiplicity distribution. So why these multiplicity distributions are important? Because once you measure this dHs deta or d and dy, that can be used as an input to this final state multiplicity. What you measure in your detector can be used as an input to calculate the initial state energy density. Okay. And what has been plotted here, this energy density times the tau, which is basically the formation time, which is again another input in your collision as a function of beam energy. And if you put tau 0 as 1 Fermi, this has been shown that in central gold collision, the energy density both in at LHC, even at in the beam energy scan at RHIC, are much higher. The initial energy densities are much higher than the critical value required for QGP production. In other words, this the measurement of charged particle multiplicity or rapidity distribution, the differential distribution is important because they will give you a hint of the initial state energy density, and in most of the cases you find at RHIC and LHC you find that the estimated energy densities are much larger than the energy required to produce a QGP, which ultimately means that QGP might have been produced in such conditions. Okay, so this ends the first part of my lecture, but then because this is the remaining part from the last lecture, from yesterday's lecture. So shall I start the next one?
So, Partha, you have 2 hours today?
No, I have 45 minutes only. But
Hello?
yes, no.
Yes, I think Siddharth is there.
Yeah.
Okay.
Yeah. So, Partha, maybe so you have one more lecture, right, Partha, tomorrow?
Yes, I have one more lecture tomorrow.
And content you have is more than that, isn't it? Will you be able to cover tomorrow? Because it's already 5:20. So because Saurav has to.
Okay, in that case, I will start tomorrow with whatever content I have, and I will go. I send you my lecture, and I think I have 25, 26 slides. I can even reduce some. I can skip some discussions, and then I will go up to which I can go in a comfortable manner.
I think that would be better because instead of putting so many things, it is better to discuss in the given time. So few things in a better way. So that will be, I think. So in case if you are not able to complete all those, then you can maybe leave some of the topics which you are planned. That would be, I think.
Okay, okay. So because tomorrow I have planned to discuss different observables, different signatures. So I will go in a manner so that I can finish. If I start a particular observable, I will finish discussion on that, and then maybe leave one of the signatures completely.
Yeah,
So,
I think that is so. In any case, you can share the slides, and if anybody, everybody can see that, and if they have further questions, they can email you.
that I can always do. No problem.
Yeah. So maybe for in 5 minutes, Partha, if you want, if there is some questions, then you can discuss. But then maybe 5:25, Saurabh can take over. So if there are questions, if not, then
Yes, please. If there are questions, you can ask.
May I ask one question? Hello.
yeah, Saurabh, yeah, yes, why not? So please.
Yeah. In your this n part scaling plot, you have mentioned that this dn yes, in this plot, this dn charge data scaled with n part for cold gold 200 GB and lead 2.76 TB, which is a geometrical effect. But
Right.
yeah, but latest result in Alice, like in xenon collision 5.44 TB, we have observed the breaking of the scaling. Means in the central collision, the multiplicity of xenon is deviated from the scaling. So is that also any geometrical effect or any other physics is there in?
That I think because xenon is a completely different system. So I didn't put that. I just put the largest heavy ion, or I want to put only the generic results which are available. So this is, I think, this is a very important question you have asked. And to the best of my knowledge, it is not. Of course, the breaking of scaling, this geometric n-part scaling, has been observed, but I don't think the exact reason for this have yet been established or have been found out. This is a 5.44 TB xenon condition.
Okay, thanks.
Maybe Partha, may I ask one small question here also?
Yes, please.
Yeah, just now I had a meeting and there we were discussing about this photon production, so PMD results in the PWG.
Right.
So there was a discussion about this. We also want to present this similar kind of result, what is shown here in your plot, but for P-led system.
Okay.
So do you like to say something on the interpretation of the result? Because there it's like the geometrical things will be entirely different. Yeah.
So P-led is entirely different than the estimation of P centrality. In P-led, people do estimation of or assigning centrality to P-led collisions is not that straightforward as in AA collisions. Because so that's why I knowingly I didn't want to include it, because this is a school, right? So it's not just a colloquium or a talk. So I didn't want to include the P-led, the centrality determination in P-led collisions. So it itself is something which is still, to my opinion or to my knowledge, is not very straightforward. So if you want, we can have later a discussion on pellet collisions.
But then you are telling that the interpretation of those results should be little bit more careful, right? One has to be a bit careful while interpreting.
Even before interpreting, the assignment of centrality to your pellet collision itself is not as straightforward as in your heavy ion collision, AA collision, right?
Right.
Assignment of those, assigning those definitions themselves are not very straightforward as it is the case for AA collision.
Okay.
So what should
Partha, looks like there are no more questions. So maybe if you can unshare and then Saurabh can take over.